of what we did in the last class. I was looking at a coplanar force system with a line distributed force. The force is distributed along a line. Two examples I considered towards the end of the class. In first example, I have an RB on which there is a line distributed force acting, okay, and this line distributed force can be represented by this function which we call as f subscript L stands for line, and then it is a function of x. What is x? X is this location, I mean the distance of a point on the RB from point A. Now given the figure that it is this FL is a triangle, I mean it is distributed like a triangle, the exact function can be written in this manner, right? You put x equals 0, FL becomes A, that is what A is here, A is given here. You put x equals B, it should become 0, and that's what is happening here. In between it is a linear variation, so that must be FL of x. Now our interest with this problem was to replace this line distributed force or line distributed force system by one single force acting at one special location. So I need to find FR, I need to find XR. I derived in the previous class that the net force FR or one single force FR that should be put there, that is just the area under the loading curve. So you look at this figure, what is the area under the loading curve? It is half times A multiplied by B. That is the area of the triangle that is appearing there. So that is FR, and it is in newtons. Force will be turned out to be in newtons. So one part is done, FR I know. Next I want to find where I should put this force, such that the equivalent force system has one single force. That's all, no torque. I derived in the last class that the XR will be the x coordinate of the centroid of the area under the loading curve. So what is the area under the loading curve? That is this triangle. It will have a centroid. Now centroid in general will be somewhere here. It will have xc comma yc, right? Both coordinates will be there for the centroid of the triangle. In this problem, yc we are not bothered about. Yc doesn't matter. This location XR is nothing but the x coordinate, only the x coordinate of the centroid. Alright. And that x coordinate will lie at b by 3. How am I getting it? I am getting it from some table. I showed you such a table 2 classes ago. If you want, you can derive that also. You know the definition of centroid of an area. If you want, you can find it now also. However, here I am referring to a table and I know it lies at xc must be b by 3. So this force must be put at b by 3 from A, and then you get the equivalent force system. A complicated force system on this side has been replaced by a simple force system on this side. One single force acting at one point. I showed another example. This example is even simpler than the previous one. Here I am saying that the line distributed force is uniformly distributed. which means that FLX is just a Newton per meter. And I have to replace this force system by again one single force acting at a particular point, that is XR. I need to find FR, I need to find XR. FR is got to be the area under the loading curve. The area under the loading curve is just A times B. It is a rectangular area. This, you get FR. XR is the X coordinate of the centroid of the area under the loading curve. We know that the centroid of a rectangle will be here and its X coordinate will be nothing but B by 2 that I put here. You replace, that is how you get the new force system. Now this force system is actually the wrench of this force system. Wrench of this force system. However, in this wrench CRW is 0. What is CRW? You will have to go back to the previous lecture and see what is CRW. CRW is the torque that you would put on the simplified force system along with FR. In this case CRW is 0, so is the case here. I have written it somewhere. Okay. Alright. Let me remove all this overwriting so that when I upload the notes it still looks readable for you. Here I use just for highlighting. Okay. Okay. So I am done with whatever I wanted to cover for the equivalent force systems. However, before I leave this topic, I want to summarize it. This topic has been spread over 3 classes and over 3 days, and that's why I want to put everything together, the major conclusions I want to summarize before leaving this topic and going to the new one. And again, this is an opportunity for you to understand the big picture, what we are trying to do with this concept of equivalent force systems. So I start from here. I am given a force system like this, which I am calling as FS1. This is my RB. A number of non-coupled forces and a number of coupled forces are acting. These double-sided arrows are the torques due to couple of forces. Single arrows are non-coupled forces acting. This is force system 1. Then the same RB is subjected to another force system, which I call as force system 2. And this force system has a number of non-coupled forces denoted by single-sided arrows, and maybe a bunch of torques arising from couple of forces denoted by this double-sided arrows. In general, 2 force systems. We call these 2 force systems as equivalent if the following 2 conditions are satisfied. The first condition is the net force from force system 1 should be equal to the net force from force system 2. That is the first condition. The second condition, and both should be satisfied. Second condition is net moment due to all forces in FS1 about a point A should be the same as the net moment due to all forces in FS2 about the same point A. Okay. Symbolically, I have been writing this. MA equals M prime A. Here A is the same point. Prime means moment due to all forces in FS2. And when I don't put any prime, it means moment due to all forces in from force system 1. A is any one point of your choice. You check these two conditions, or rather condition B only for one point A, and that is enough. And that point A is your choice. That will mean if both our conditions are satisfied, we will say that the two force systems are equivalent. Okay. Then I talked about a special type of equivalent force system in which I insist that there is only one single force acting at a point of my choice. Whatever point I choose, I should be able to put one single FR and an associated torque such that this system and this system become equivalent. What is the advantage of going from here to here? Simplified force system. The second force system has just one single force, one single torque, whereas my original force system may be having numerous thousands of forces and 10,000s of torque. I don't want to keep dealing with so many forces, so many torques, so I would like to get such a nice simple force system. And the point is of my choice. My friend comes and says that I also want to get a force system which has only one single force, only one single torque, but I want to put the force at point B, not at A. My friend's favorite point is point B. He can also have such a force system. He will put the same FR what I have here, he will put at B, and then he will have to put a CRB, a torque, CRB. And note that CRA and CRB are not the same. They are related, there is some relationship, but they are not the same. What exactly is the relationship is a detail which has already been covered in the previous lecture. Okay, this is what we did. Then I went one step further and I said that is it possible to have an equivalent force system in which I will have one single force indeed, and that force will still be FR, but the torque that I will have to put, which I am calling as CRW, that is completely along FR. I am raising this curiosity. Is it possible to have such an equivalent force system? The answer is it is possible. You can have such a force system in which CRW will become parallel to FR, but the only compromise is the point W is not for you to choose. It's not an arbitrary choice. Point W will come from an equation, which again is a higher level detail. Go back and see the lecture note. You find W and then you put FR, and then you will also find CRW. You will know the value, but CRW will be guaranteed to be parallel to FR. Such a force system is called the wrench of the original force system. जहां से भी start किया था, whatever was your original force system, this will be called the wrench of that original force system. Such a force system, the wrench of the original force system, is the simplest force system that you can think about, given that the original force system is three-dimensional in nature. What I mean by three-dimensional in nature, no restriction on the direction of Fi's and Cj's. All forces in the original force system are oriented in all sorts of directions. All Cj's are oriented in all sorts of direction, and that is what I call as a general three-dimensional force system. For a general three-dimensional force system, this is the simplest resultant force system or simplest equivalent force system you can arrive at. Okay, wrench. All right. However, there are some special types of force systems. Now I am talking about special types. I am not talking about general three-dimensional force systems. There are some special types of force systems in which you can actually get the wrench in which even CRW is equal to 0. What does it mean? It means that the simplest force system will have just one single force Fr acting at a special point W. That is possible for some special types of force systems. I gave you two examples of such special types of force system. One is the coplanar force system and the other is the parallel force system. At least in this course, we considered two special cases. All right. Now, what is a coplanar force system? What is a parallel force system? Go back to the notes, watch the video, and see the details there. Since it is a summary, I don't want to go beyond this point, except to say that these two examples with which I started today's lecture, these are both are coplanar force systems. Both are parallel force systems also. I mean, it's coincidental that these examples are not only parallel force systems, they are also coplanar force system. All right. And hence, in these cases, I was able to get the resultant force system with one single force only, and CRW is 0. And this point, what we are getting is actually W. Similarly, in the other case. Okay. All right. Fine. So this was my summary, and with this I complete my topic on equivalent force systems. Ready to start a new topic? If you have any questions, please ask. Don't have any question, I would like to move ahead. What is the next topic? The next topic is relationship between external force system acting on an RB and the consequent motion of an RB. That is what we want to address. Okay. We are looking for some relationships that have one side force system and on the other side we have consequent motion. Now see, after all, what we want to predict, we want to, if there is an RB and I have a force system acting on it, external force system, what do I eventually want to predict? I want to predict at a later time, at say at time t, I want to know so this is the reference frame, this is the origin, this is the reference frame of interest, this is my origin, and then I have these three frame embedded unit vectors mutually perpendicular unit vectors. I want to know at any arbitrary time t so this is body M. I want to know this one point of the RB, how far it is from my origin at time t. This I want to know. Also, I want to know okay, here I have E1, E2, E3 fixed to F. Small e1, small e2, small e3 make a triad, mutually perpendicular unit vectors fixed to the body. So beside this RPOT, I want to know how E1, E2, E3 are oriented with respect to big E1, big E2, big E3 at time t. If you know this and you know this, think about it, you know exactly, you have the complete description of the RB motion. You know where one of its point is lying and how the small e1, e2, e3 are oriented with respect to big e1, e2, e3. That will be enough to completely describe the motion of this RB. Now, somehow if I know AAF, what is AAF? Acceleration of point A with respect to frame F. If somehow I know AAF, I can time integrate it to get VAF. And if I know VAF, I can time integrate it to get R. Okay, here I made a mistake. I should not write P here. Should write A. There is no P here. Yeah. So you know AF, time integrate, you get VAF, time integrate, you get RAO. T. So this is the roadmap. If somehow one can tell me acceleration of A, I can find velocity and then I can find RAO. One part can be known like that. Now if you come to the second part, how the orientation can be found, if somehow we know omega dot mf. Omega dot mf is the angular acceleration of the body. I can try to go from angular acceleration to angular velocity, right? And then from angular velocity I can go to orientation of small e1, small e2 and small e3. Again there will be time integration involved. Okay. So the relationship that we are looking for between the external force system and the motion can be something which relates acceleration of A to the net force, and a relationship that relates angular acceleration to the force system. Indeed, that relationship, there is a set of two relationships that we know, and we use those relationships to predict the motion of an RB, and those relationships are what we call as the Euler's axioms. The Euler's first axiom, there are two axioms. The first axiom is Euler's first axiom says that where F is net force, rather net external force acting on the RB. So we have force or a force related quantity on the left hand side. What is M? M is the mass of the RB. Mass of the RB. And what is ACI? ACI is, before ACI, I should say C, what is appearing here is the center of mass of RB. Okay, and what is I? I is a reference frame, but a special reference frame. It is an inertial reference frame. Inertial reference frame. Let's draw a diagram here to have a better visualization. This is center of mass of the body. This is RBM. And again I am using M as the name of the RB, and M is also the mass of the RB. So it will be clear from the context what M stands for. And then I have an inertial frame I. Here I have a point O which is fixed in I. This is Euler's first axiom. You think about it, it is doing exactly what I was expecting here. I said that if I know the acceleration of one point, or if I can relate the acceleration of one point on the RB to force or something related to force, I can find acceleration of that point, and then I can time integrate, get velocity, and then get position vector. On this slide I was expecting A to be any point. However, the Euler's first axiom is very clear that the point whose acceleration will appear in this relationship is not any point. It is a special point. It is the center of mass of the RB. Okay, and of course ACI is acceleration of Cm of RB with respect to I. This is Euler's first axiom. Note that this is a vector equation. It is a vector equation. Okay, you can extract three scalar equations out of it. Three scalar equations. So it is can be obtained. So if your working coordinate system is Cartesian coordinate system, you can get three scalar equations out of it. This is Euler's first axiom. There is another axiom, goes by the name of the same scientist, Euler's second axiom, and what Euler's second axiom tells us. Symbolically, this is what it tells us. Again, let's have the figure, which should be the same figure what I drew on the previous slide. This is frame I, and this is RBM. Here, what is MO? MO is the net moment due to all external forces. All external forces and torques about point O, where O is fixed in I. I hope this sentence is meaningful. I have defined how moment due to all external forces can be computed. I have been talking about MA, M prime A, right? So we know how to find MO. Then on the left hand side, I have time derivative of a vector with respect to I, and that vector itself is HOI. What is HOI? I wonder if you remember. 2 classes ago, I defined a quantity for which I used this symbol. What is HOI? HOI is the angular momentum of the RB about point O and with respect to frame I. Where I is again an inertial reference frame. Inertial reference frame. This is the second axiom. This is also a vector equation, right? Moment will be a vector. Angular momentum is a vector. Rate of change of angular momentum will be yet another vector. So it is a vector equation. And again, if you use a coordinate system as your working coordinate system, that this will lead to 3 scalar equations. So these 2 equations we will use Euler's first axiom and second axiom to arrive at a position where we can predict the motion of an RB. Given a force system, what will be the motion of an RB, that story or that relationship is ingrained in these two axioms. We will use it extensively during the remaining part of the course. Okay. All right. Let's see what we have next. Now, while telling you about the two Euler's axiom, I have put a restriction on the reference frame in context. Now we are saying that forces and acceleration, forces and angular momentum, they are related, but the frame in context has to be a special frame. It has to be an inertial reference frame. I am sure you have heard this phrase before, but I will pretend that this is the first time we are coming across this inertial reference frame. I don't know what your understanding of inertial reference frame is so far, but I will pretend we don't know anything and I will define what an inertial reference frame is. And the definition of this frame is somewhat funny in the sense that we say that a reference frame is inertial if Euler's first and second axiom are found to be true for all rigid bodies. That's the definition. In other words, what Euler's axioms are telling us that there exists a frame I in which the rate of change of momentum of the RB about 0.0 will be the net moment due to all forces, and the net force acting on the RB will be mass times acceleration of the center of mass of the frame with respect to I. There exists a frame. How do we find that frame? This prescription is not there. Okay. So that's why I said it's a self-serving definition. Euler is giving axioms and then saying that it is true in inertial frame. And when you ask what is an inertial frame, he says that the frame in which my axioms are true. Okay. So that is what it's somewhat funny. Now let's have a look at this. I don't know how clear it is on your side what I am showing on the slide. Rishabh, is it readable? It's not very high resolution. It's not readable. Okay. Yeah. Zooming will not help. What I will do is I will read aloud, and then in the PDF file I will just read it aloud for the time being. Hello, is it? Yeah, I am saying that zooming will not help because the resolution is inherently poor. So yeah, so what I will do, I will read the text right now, and then in the PDF file I know it will be readable because I have a PDF file. I can read it on my computer, so students will be able to read it eventually. For the time being, I will just read it aloud. So this is some text that I have copied from this book, Dumir, Sengupta and Veeravalli By the way, this is the textbook that I prescribed for this course. Page number 132. It's a very interesting reading. It's about finding an inertial reference frame. So if we want to use Euler's axioms, we will have to first find an inertial reference frame, right? And this text is about that. This part of this text starts with a statement: it is impossible to find an exactly inertial physical frame. It is impossible. However, in order of decreasing accuracy, the following four physical frames are commonly used as inertial reference frames. Okay, so as engineers and even as for our research as well as engineering problems, this is what the community has decided as far as the choice of inertial reference frame is concerned. There are four options that you can use, four reference frames that you can choose to be inertial, but their order of accuracy will be different. The order of accuracy is going down as we go from 1 to 2 to 3 to 4. What is the first inertial frame that we use as scientists and engineers? Frame attached to the center of mass of the solar system with its orientation, and when they say orientation, they mean orientation of a triad fixed to it, the same kind of triad, big E1, big E2 and big E3 that I have been using in my lectures. Frame attached to the center of mass of the solar system with its orientation fixed relative to specified distant stars. These distant stars are called fixed stars since they are so remote that no change has been observed in their angular separation ever since human beings started making observations. This is used to describe the motion of tides, astronomical bodies and interplanetary rockets. So if we are planning to send a rocket to Saturn, we will apply Euler's axiom because our rockets will be treated as rigid bodies, so we will need Euler's axiom. Euler's axiom will need an inertial reference frame, and for that kind of application, astronomical bodies, interplanetary bodies, this is the inertial reference frame that we have been using. That reference frame is attached to the center of mass of the solar system, and there are three stars which we have chosen, and the three triads big E1, big E2 and big E3 are pointing towards those three specific stars. And we treat those stars as fixed stars because they are very far and we have not observed any change in their location. That's number one choice. Number two, frame attached to the sun center with orientation fixed relative to distant stars. Frame attached to sun center, whereas the first frame was attached to the center of mass of the solar system itself. That is more accurate than the second one. Third frame attached to the earth center with orientation fixed relative to distant stars. The third reference frame can be treated as an inertial reference frame to describe the motion of trade winds, cyclones, ocean currents, long-range missiles and rockets which have long-distance motion near the Earth's surface. However, sometimes this frame is needed even for small-range motion. Now there are some more details. I don't want to go that far. Ignore this statement. So the third reference frame is attached to Earth center and its triad pointing to distant stars. The fourth reference frame is attached to the Earth and rotating with it at constant angular velocity relative to frame in item 3. The fourth frame yields excellent results for almost all dynamic problems in engineering where the range of motion is small compared to the Earth's radius, such as turbines, machine dynamics, automobiles, and channel flows. That's the fourth reference frame, which is essentially attached to Earth. Okay. Four choices we have. First one is the most accurate, fourth is the least accurate. But then for day-to-day engineering problems, this book is telling us that the fourth frame is adequately accurate, and this is what we use for motion of such small objects near the Earth's surface. Okay. In this course, we will entirely rely on this number 4, which is an Earth fixed reference frame. But keep in mind that if your application changes, if you have to send a rocket to Saturn, you have to send a rocket to Pluto, then you should not use this reference frame. You should rather use number 1 reference frame, because that would be more accurate. That is more inertial, in a manner of speaking, more inertial than number 4. Alright, so I stop here. We take a break. We will meet at 5 past 5. So let's have a quick recap